Hey there, this is Ivan and Juliet making the demonstration for our project on recording RSSI data in AO2.11 networks using COTS devices. The project consists of a Linux command line front-end utility that provides the user with an interface to a set of modules that collect and record RSSI values reported by a wireless network card's device driver. We're using a Raspberry Pi to receive Wi-Fi signals from a wireless router. The user controls the program from the command line of the Raspberry Pi. This diagram is showing how the user interfaces with the recording software. The recording software sends packets to the router and receives the response back with updates of the RSSI data. The recording software also stores signal levels into the data storage location. This is a general sequence of what's going to happen when we run our recording software program. So this is what's going to be happening behind the scenes. Now we're going to move to demonstrate how the signal levels change as we move between the Raspberry Pi and the router.
All right, so just like in our physical diagram, we have a user, we have the Raspberry Pi, and then over here we have wireless router. The wireless router and Raspberry Pi are connected and sending signals back and forth between each other. All right, program is command line interface, and here in this window we've got like all the commands that are available in the help section. I'm going to show you here. This is an example of output from command line, and it's displaying it to the screen, which is an option. You can see the RSSI values updating. I've got it at every 100 milliseconds. It's taking a reading, and it's currently set to take 10,000 readings, but we're going to cancel that now. And just to show here, there's a log file that it generated. And as you can see, same values that were seen before. All right, and I wanted to show the actual action as it works. So I'm going to be moving between the Raspberry Pi and the router, and we're going to get changes in the RF field. So let's go and make this full screen, and just watch the value, watch the bouncing line. It's not up. See it stabilizing, and somebody moves between it, and block it completely, and it just drops off. So this data here can be used for analytics, detection of motion, variety of other things that we covered in the rest of the presentation. All right, thank you.
Now that we have demonstrated live how our program reacts when there is an obstruction between the Raspberry Pi and the router, we're going to show you some tables of 3 different scenarios that were recorded as we run our programs doing different tests. So this first table just represents a stable signal when there's no obstruction in the RF field. Okay, these graphs represent when we introduce an obstructing body into the RF field. And finally, this graph represents an obstructing body moving in the RF field. Clearly, there is more movement in the graph because the RF field is being obstructed, and you can see the difference between when there's no obstruction in the RF field, when there is an obstructing body without moving, and when there is an obstructing body that's moving. We believe that RSSI is a viable source of monitoring data. However, after testing the software multiple times, we have concluded that the RSSI values that we recorded with the project's approach have limited accuracy. So to end, we would like to make some recommendations if someone's willing to take on in our project, which we really encourage you because it's really interesting. We have learned a lot from this, especially how important it is and how our results were not as accurate as we would like them to be. So the first recommendation that we're going to give you in case you want to keep doing this project is to change from RSSI values to CSI values, because this should most likely produce more accurate results. They will also like to recommend the use of a mesh network instead of a Wi-Fi regular network, because this will most likely present opportunities for whole environment monitoring and overlapping and cooperative area fields. One of the mesh networks you could use could be 802.11ac. I believe that the use of the mesh network will produce much richer data sets for using machine learning algorithms and will allow multi-node padding, which presents opportunity for employing trilateration techniques. Another recommendation that has nothing to do with accuracy, but like it will be better, it will make the project better, would be to maybe rewrite the program in C or C++. Also, to use direct calls to the Linux networking kernel. Finally, we'll recommend the use of buffers or any other memory structures, because this could minimize how many times the file system is accessed. Altogether, as I stated already, the main problem with the program is the accuracy of the results, but we have already given you some advice in how this could be improved. Thank you.